This tutorial will be a review for Chem 111 Exam 3. In this particular one, we will be focusing on stoichiometry. So what is stoichiometry? Stoichiometry shows the prediction of both the reactants and the products. So in other words, it shows you how much you can actually create in a chemical reaction. It can also show you how much you need of the other reactants. So it shows you both. It also is a way to show relationships between things. So why do we need a balanced chemical equation? That is a result of the conservation of matter. What this is saying is whatever you have at the beginning, you have to have at the end. You can't lose any atoms. You can't lose any compounds in the process. So the balanced chemical equation is a way to keep track of everything that's being involved. The coefficients are the numbers in front of the chemical reactions, in front of the chemical compounds, to show that it is a balanced chemical equation. So they are the whole number ratios. So it's the whole number ratio that is used to balance the chemical equation. The limiting reagent is the reactant that is completely 100% used up, and it determines the theoretical yield. The limiting reagent is the reactant that's completely used up, and it determines the theoretical yield. The excess reagent is stuff left over. It is not 100% used up. You have stuff that's remaining at the end. The actual yield, so the limiting reagent determines the theoretical yield. The actual yield is after an experiment has actually occurred. So that is your real value. So you're in the laboratory, for instance, and you take measurements at the very, very end, and you want to know how much you have that you actually made. That would be the actual yield. And then the percent yield is the percentage between the actual and the theoretical. So that's actual over the theoretical times 100 to make it a percentage. So what you actually got in lab divided by how much you could have gotten in lab times 100. The actual yield will have to be given to you, or that you're actually in lab and you measure. Whereas the theoretical is what you calculate. Alright, so let's do some practice problems. We have several practice problems with these just to make sure we're all on the same page and knowing what we're supposed to do. So how many moles of IF5, so here's IF5 and we want moles, produced using 44.01 moles of I2O5 and 101.0 moles of BRF3. Alright, so notice that we have two things on the left hand side. That means, and they're asking about something on the right hand side. That means that we have to figure out the limiting reagent before we can determine the actual maximum. Because the number, if you convert both of them over, you're going to have two different numbers. And the number that is the smallest is going to be how much you could possibly produce, which means that will be your theoretical yield. So we're going to take this as two different problems. So we're going to look at one at a time. I'm going to do I2O5 first. So I'm going to cross that one out for now. And I'm just going to focus on 44.01 moles of I2O5. All right, so in order to go from one compound to another, I have to go through moles first. So if it was in grams or if it was in liters, I would have to convert it over to moles before I can do the conversion. All right, so I'm already in moles, so I don't have to worry about converting it to moles. So to go from moles of one to moles of another, I use the coefficients. Which is the 6 and the 12. Now what that question is asking me for is moles. So that means I don't have to convert it again. I can just use one set of brackets and I'll be fine. So 44.0 moles of I2O5 over 1, because I want to make it into a fraction. I'm going to multiply it by another fraction. I have I2O5 on the top. That's what I want to put on the bottom of the next one. The coefficient 6 means that 6 goes on the bottom. Moles to moles is the only time you ever use these coefficients. In any other bracket, you do not use, or any other division sign, however you want to say it, you do not use the coefficients. It's only in this particular where you go from moles of one thing to moles of another. Just the horizontal line here. I'll show you what I mean as we go into more examples. So 44.0 times 12 divided by 6. That comes out to be 88.0 of IF5. Alright, so that's one option. Let's do the conversion of the next one. We now have 101.0. And we're still looking for the moles of IF5. Once again, we have moles to moles, so I'm going to use the coefficient, and that's all I'm going to use. So 101.0 moles of BRF3 over 1. BRF3 on the top. I'm going to put BRF3 on the bottom of the next line. I'm using the coefficients because I have moles to moles. So 20 moles goes on bottom. Then on the top, I'm converting it to IF5. So 12 moles of IF5 go on the top. So it'd be 101.0 times 12 divided by 20. The BRF3 cancels out, and I'm left over with IF5. And that comes out to be 60.6 moles of IF5. Alright, so now, since I had two at the beginning, since I had two questions at the beginning, I'm going back to the previous one, and I see I had 88.0 moles, and the new one I had 60.6 moles. 60.6 is smaller, so that means that's the theoretical yield. Whenever you're given information about more than one of the reactants, you automatically have to convert both to figure out which one is smaller. So this is our theoretical yield, which means that this is how much you could possibly produce. It also means, if the question were to ask for it, that this BRF3 would have been the limiting reagent and I2O5 would have been the excess reagent. Alright, let's try another one. There are 10 grams of sucrose and 10 grams of oxygen reacting. Which is the limiting reagent? So this one's specifically asking about the limiting reagent. Once again, they give you amounts for both of them, so we're going to do them as two separate equations. So sucrose is this C12H22. and they want to know which one's the limiting reagent. There's a couple different ways to go about doing this. How I prefer doing it is I like to pick a product to convert both of them to so I can compare them. So I'm going to compare it to the CO2. I'm only going to convert it over to moles because I don't really care how much mass I have left. All I care about is which one's my limiting. However, I'm starting off in grams this time. In order to go from moles of one to moles of in order to go from one compound to another compound, I have to go through moles. I have to go from moles of one to moles of the other. So in order to go from grams to moles, I'm going to need the molar mass of C12H22O11. So I have 12 carbons at 12.0 grams. That comes out to be 144. I have 22 hydrogens times 1 for the mass of hydrogen. So that comes out to be 22. And I have 11 oxygens. I'm getting these numbers right here. Which oxygen is 16. That comes out to be 176. We add those together, and that comes out to be 342 grams per mole. This was the carbon, this is the hydrogen, this is the oxygen. Alright, so I now know that I can use the molar mass to do grams to moles of the sucrose. Now to go from moles to moles, I use the coefficients in the balanced chemical equation, and that'll give me moles of the CO2, which is what I'm looking for, so I can stop there. I don't have to convert it back to grams. Pay attention to what the units are telling you. The units will guide you through the problem. So 10.0 grams C12H22O11 over 1. We have grams on the top, so I'm going to put grams on the bottom of that exact same compound. And that's 342. And that is 1 mole of C12H22O11. Notice it's 1 mole. I had alluded to that in the previous question. I specifically said only use the coefficients for when you go from moles to moles. This time we're going from grams to moles. So we do not use those coefficients. Okay, so now that we're in moles of C2H22O11, I'm going to use the coefficients to get to moles of the other. So up here we have 1 mole and we are going to 12. So 10 divided by 342 times 12, that comes out to be 0.351 moles CO2. Alright, so let's convert the next one. We're starting with 10 grams of oxygen. And I'm going to convert once again to moles of CO2 so I can compare the two numbers. Once again, I have grams, so that means I need to go to grams to moles first before I can use the coefficients. That means I need to figure out the molar mass. So oxygen is 2 times 16, which is 32. That's going to be my molar mass I'm going to use for this. I got the 2 from the oxygen here. I got the 16 from the molar mass down here. Alright, once I get to moles, I can go to moles using the coefficients, which are the numbers out here, the 12 and the 12. Okay, so 10.0 grams of O2 over 1. We have grams of O2, which means I want to put grams of O2 on the bottom of the next one. That's going to be 32. That is equal to 1 mole. Once again, notice I'm using 1 here. I'm not using 12, I'm using 1. The only time I ever use those 12s and those coefficients is when I'm going from moles to moles. Here I'm going from grams to moles. So I use 1 for moles. Now I use the coefficients. I have moles of O2 on the top. That means I want to put moles of O2 on the bottom. The coefficient for it is 12. I'm going to CO2, so I'm going to use 12 moles of CO2 on the top. So 10 divided by 32 times 12 divided by 12, that's going to come out to be 0.313 moles of CO2. Alright, it was asking for the limiting reagent. So that means I need to figure out which one was smaller. I have 0.313 on this one, and I have 0.351 on this one. So that means that this one is smaller, which means that made the theoretical yield of 0.313 moles. The limiting reagents, as I said at the very beginning, is what determines the theoretical yield. So that means this is the limiting reagent. Because it produced the smaller of the two numbers. Alright, let's try another one. Aluminum reacts with chlorine gas to form aluminum chloride via the following reaction. 2Al plus 3Cl2 yields 2AlCl3. How many grams of aluminum chloride, so I'm looking for the grams of aluminum chloride, produced from 34.0 grams of aluminum and 39.0 grams of chlorine gas. Now keep in mind that I have two reagents. I have numbers for both of them. So that means I have two different reactions here. I have two different calculations here. Also keep in mind that if you by chance only have one there, you only have to do it once. I'm only doing it twice because I have two different numbers. Alright, so from here, I'm starting off with grams. In order to go from one compound to another, I have to get to moles first. So I need to go from grams to moles. I look for aluminum, and I see that it's 26.98 grams per mole. Moles to moles, we use the coefficients. Now that we have it in moles, we can use the coefficients. The question is actually asking for grams, so I need to convert it back to grams, which means I need to figure out the molar mass of AlCl3. So I have Al and I have Cl. I have 1 aluminum and 3 chlorines. Aluminum is 26.98. Chlorine is 35.45. That's going to equal 26.98 plus 35.45 times 3, which comes out to be 130.3 grams per mole. Alright, now that I have the molar masses, so this will be 130.3. I can set up the equation. So 34.0 grams of aluminum over 1. I have grams of aluminum on the top, so I need grams of aluminum on the bottom of the next one. To go from grams to moles, I need to use the molar mass of 26.98 grams. That is 1 mole, because I'm not going to moles, I'm going grams to moles. Now I need to go moles to moles. So I have moles of aluminum on the top. That means I need to put moles of aluminum on the bottom of the next one. The coefficient for that is a 2. Then we're going to moles of AlCl3. The coefficient for that is 2. 1 mole of AlCl3 is 130.3 grams. I'm running out of room. I apologize. Alright, so it's 34.0 divided by 26.98 times 2 divided by 2 times 130.3. That comes out to be 148 grams of AlCl3. We're going to do the exact same process, but now we're going to start with chlorine gas. So 39.0 grams, and we want to know how many grams of AlCl3. So for this, we need to go from grams to moles. We do that by using the molar mass. So we have Cl2, so 2 times 35.45. That comes out to be 70.9. Then moles to moles, using the coefficients, and then moles to grams, using the molar mass of AlCl3, which we got in the previous question, to be 130.3. We can set this up now. We're starting off with 39.0 grams of chlorine over 1. We have grams of chlorine on the top, which means we want to put grams of chlorine on the bottom in the next one. That tells us that we need the molar mass. 70.9 is in 1 mole. So we have moles of Cl2 on the top. We put moles of Cl2 on the bottom of the next one. Now we're in moles, so we can use the coefficients. So the moles for Cl2 is 3, and the moles for AlCl3 is 2. Once again, I only use the coefficients when I have moles to moles. Whenever I don't have that, no grams per mole, 1 goes with the moles. I don't use the coefficients. The only time those coefficients ever come in handy is moles to moles. Alright, so we have it in moles of AlCl3 now. I'm going back to 1 for the moles, because the coefficient, the moles to moles, is the only time I ever use it. I'm going to grams now, to 130.3 grams of AlCl3. That's going to come to 39.0 divided by 70.9 times 2 divided by 3 times 130.3. That comes out to be 47.8 grams of AlCl3. From here, we need to compare. The previous one was 148 grams. This one's 47.8 grams. So this one is smaller. So that means this one's going to be our theoretical yield. So it's saying how many grams of aluminum chloride could be produced. Well, the smaller of the two numbers is how much you can produce. That's your theoretical yield. Remember, your limiting reagent is what gave you your theoretical yield. So the Cl2 would then be limiting reagent. The other one would then be your excess reagent. A lot of times I do XS like that. And then this would be your product. We're going to do 2 more examples and then we'll be all done. Alright. In this reaction, CaCO3 and 2HCl yield CaCl2 and CO2 and H2O. 6.088 grams of CaCO3 react with 2.852 grams of HCl. What mass of CaCO3 remains unreacted? They're telling you from the start that there's going to be leftover calcium carbonate. The fact that they're telling you that means that this will be your excess one. So you do not have to convert both of these. HCl will automatically be the smaller one. It's telling you that there's going to be some left over. So that means that this one, the HCl, is your limiting reagent. So that means that's the number we're going to have to deal with. So we're going to go from 2.852 grams of HCl. We're going to convert that to moles by using the molar mass. So we have H and Cl. Our H is, we have one of them times 1.0. Cl is 1 times 35.45. So this comes out to be 36.45 grams per mole. That gives us the molar mass of the HCl. Then we go from moles to moles using the coefficients from the balanced chemical equations. Then we go from moles to grams of calcium carbonate by we see grams, so that tells us that we need to figure out the molar mass of the CaCO3. So we have calcium, carbon, and oxygen. We have 1 calcium, 1 carbon, and 3 oxygens. Calcium is right here, it's 40.1. Carbon is right here, it's 12.011. And then oxygen is right here, it's 16.0. Add those up, and it comes out to be 100.1. Alright, so we start off with the 2.852. The molar mass of HCl is 36.45, and that's 1 mole of HCl. Then we use the coefficients, 2 and 1, so 2 moles of HCl and 1 mole of CaCO3. And then the molar mass of calcium carbonate, which is 100.1. And once again, I ran out of room. So 2.85 divided by 36.45 times 1 divided by 2 times 100.1, that comes out to be 3.916. If we're starting off with 6.088 and we only use 3.916, that means we can determine how much we have left over by subtracting the 2. And that comes out to be 2.172 grams. That's how you determine how much is left over. You have to convert it over to how much you would be using and then subtract it off. This will be our final practice for this review. What is the percent yield of the following reaction if 60 grams of the calcium carbonate is heated to give 15 grams of calcium oxide? So notice that they gave you numbers on both sides of the equation. This is your actual yield. You do not use that until the very, very end. So you convert it over just like we did here, where it goes grams to moles, moles to moles, moles to grams, and then you're going to compare that one. So we don't even need this right now. It may seem confusing to you, but once again, if you have numbers on both sides of the arrow, that means that you're given the actual yield on the right-hand side, and you want to compare it later. So we got to go from grams to moles by using the molar mass. We solved that one in the previous problem, so I'm going to use that again. It was 100.1 grams per mole. Then we go from moles to moles of the calcium oxide by using the coefficients. And then we go from moles to grams of the calcium oxide by using the molar mass. And that molar mass is 56.1. Calcium is here, it's 40.1. Oxygen is here, 16.0. So 16 plus 40, that's how we get 56. Alright, so 60 grams of CaCO3 over 1. Grams on top, so we're going to put grams on the bottom, which is 100.1 grams of CaCO3, then 1 mole of CaCO3. Moles of CaCO3 on the top, so that's what I want to put on the bottom. And that is 1. The coefficient for CaO is also 1. One mole of CaO is 56.1 grams. And that'll tell me how many grams that I should have been able to produce, how much my theoretical would have been. So that's 60 divided by 100.1 times 1 divided by 1 times 56.1. That comes out to be 33.6 grams for your theoretical yield. Now, to get the percent yield, it's going to be what you actually got divided by the theoretical. So that comes down to be the actual is 15 divided by 33.6 times 100. That comes down to be 44% yield. Keep in mind, it might not actually say the actual yield was da 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 da. It'll just simply say this is how much was produced. For instance, this one says to give 15 grams. So that means at the end of it, you had 15 grams. So they want to know how much percentage of what you were supposed to get did you actually get. And that is the end of the review for the Chem 111 Exam 3, Part 1.